Welcome everyone. So today we'll talk a bit about dodging and how we are going to invert the divergence while preserving spatial support. But before that, we'll talk a bit about the exercises. So last time I asked you, can you find me a function which is, say, I asked periodic, but it doesn't really matter. Let's say find me a function from which is supported in -1, 1. So let's call it phi, such which goes from R to R, and phi is smooth, compactly supported in R, and support phi is in -1, 1. And I wanted to find a primitive of this. So I wanted to be able to solve or find a psi such that dx psi is phi. Okay. And such that the psi also has compact support and is in the same interval. Okay, so this was part of the first exercise last time. I mean, I don't know, can someone tell me like what such a function is? I mean, this is easy. Don't be shy. Epsilon equals 1, sorry. No, but there are no modifiers here. This is just, I want to find a function. Yeah. Yeah, okay, but that's compactly supported. Okay, I don't think so are you talking about a function that looks like this, basically? Or no? Sorry, I didn't understand. Okay. It's always positive. No, but the problem with something always positive is that if you solve this, I mean, you can solve this by integrating from any point here onwards. And if you do that, you see that the function psi will be something that is 0, but then it will start increasing, and then it will just be this constant afterwards, right? And so this psi won't satisfy the property that its support is also contained. So yeah, no, but that's again positive, right? I mean, so anything positive won't work because its integral will be positive, and so then after 1, the value of psi will be positive, right? So a condition you can ask for is sorry. Something you can ask for is if I want the mean of phi dx to be 0, then indeed you can do this. So let's say this was the exercise. I chose something like this. Then indeed, if I take a primitive of it, which in this case in 1 dimension is just taking the integral from some negative number, this will still preserve the support. All right. But what we want to do, and we'll see this, is we'll want to take successive many primitives of this guy. So now what we want, and this will be relevant when we do the localized inverse divergence. We'll want something like, we want to take, we want to find a psi such that if I take dx to the power n, so let n be some natural number, which is this to be large, dn of psi is phi, and moreover, the support is contained -1, 1. Okay, so you'll see quite easily that something naive like this will not work, because you can take one primitive of this guy and you can check that this will look something like this. But in order to take the next primitive, this again has to be mean 0. And only then you can take another primitive while keeping the support. So it turns out that the condition to have this is so that enough moments of phi vanish. So if x to the like dx equals 0 for all n, let's say, from 0 to this, let's say, capital N. If all of these vanish, then you can actually take successive primitives. And this will be like an exercise for you guys. So show this. All right. And now we are kind of going to use this in order to construct our okay. So for this, I guess I'll call it like a lemma/exercise. So let f be a smooth function on R2. Okay, so maybe let me just clarify what we are trying to do. Previously, we saw that our perturbation consists of these flows, these Mikado flows. Right, so these guys, which are W's, and these have the property that in this direction, so they come with the direction psi. So in this direction, they are constant. So essentially, they are a function of the orthogonal plane to psi. Right, so they are a function of two variables in this plane. And so that's why in this lemma, we are going to work with functions on the plane. All right, be smooth. And then consider this phi. And let's make a modifier out of it. So let phi lambda, let me put a tilde on it, x or c dot just be lambda psi lambda c dot. All right. And let me now, so this is still a function of one variable. Let me make a function of two variables from this. So let's call phi, maybe I'll put a bar of lambda of x1 comma x2. This I'll call as psi tilde lambda x1 times psi tilde lambda of x2. Right, so this is just a definition. And now I can define my projection. So I'll define the version of this Littlewood-Paley projection that I want to use, but the one which preserves which preserves support to be this. So projection onto, let's say, lambda. Let me call it a tilde just or a bar just to distinguish it from usual Littlewood-Paley of f. is just going to be the integral on R2 of this phi bar lambda y f of x minus y. So this is just modification of f, against psi dot. Okay, and now, like in the classical Little-Paley decomposition, we can now have a decomposition of f as follows. So f decomposes as you have the identity function minus no, this is still fine. Projection onto some, let's say, let me just call it n bar, f plus projection onto lambda n bar minus projection onto lambda n bar minus 1 f plus until some let me call this 1, and all of these have these bars. Okay, so I've not done anything here. I've just taken a telescoping sum, and with just the property that if I have f is periodized to some period, or if you want, if f has mean 0, and this guy, if you want, you can just take it to be the mean. Then this is actually an identity, and this gives a decomposition of f. Okay, but what is the purpose of this? So the purpose of this is these guys preserve the support of f. So I guess the first thing you want to show that the support of one of these guys. So let me call one of these guys. Let me denote by p lambda lambda 1, lambda 2, let's say, as just p of lambda 2 minus p of lambda 1. Yep. And so show that the support of p of lambda 1, lambda 2, f is contained in a ball around the support of f with radius given by lambda 1 inverse. Right? So this is an exercise, and you can, this is showing that when you project, when you basically mollify along with these mollifiers, they preserve the support that you want. All right. Okay, and now the next bit will be show that there's a nice inverse divergence for this. So show there exists a tensor, let me call it capital theta f lambda 1, lambda 2. So this will be a tensor, so it takes values in, let's say, from R2 and spits out something in R to the 2 to the D. To the n, did I call it n? I called it n. All right, such that if I take successive divergences of this, so divergence to the n of this theta f lambda 1, lambda 2, this is equal to this projection e of lambda 1, lambda 2. And moreover, this has the same support property as this. And support of this theta is contained in the same thing, a ball around the support f of radius lambda 1 inverse. Okay, so the second part is a bit challenging, so I'll give a few hints over there on how like the steps of this can go, but part one is quite easy, just from definitions. Right.
Lambda is increasing.
The lambda is increasing, yeah, thank you. Yeah, lambda 0. Okay. And I guess kind of a hint for this is, so let's write it here. Okay, is to first consider this function. So the modifier associated, I mean, the kernel associated with this projection operator will be given by phi lambda 2 x1 phi lambda 2 x2, and then you have minus phi lambda 1 x1 phi lambda 2 x lambda 1 in x2. And now we just add and subtract. Let's see, what's the correct thing to add and subtract? Let's say phi lambda 1 in x1, phi lambda 2 x2, and then I have to add it back. Phi. All right, and so now I'm just going to group this together and group this together. Right, and both are of this form. So now you'll use the first part of the exercise to find a psi lambda 1 of, let me call it x1, such that if I take dx, so x is this parameter here, to the n, I get phi, this difference. Phi lambda 2, maybe I should call it lambda 1, lambda 2. Phi lambda 2 x1 minus phi lambda 1 x1. Okay, this is just using the first part of the exercise. All right, and now the claim is if I define a tensor theta such that the the all ones component of it is given by this psi lambda 1 lambda 2 x1, and then I have phi lambda 2 x2, and the one which is all 2's. So remember, like we're working in 2 dimensions. So scalars are just real numbers. Vectors are things with 2 components. 2 tensors are things with 4 components, and so on. And so n tensors are indexed by n components, each of which can either be 1 or 2, corresponding to the 2 components of the tensor. So this guy will be the other one. So phi lambda 1 x1, and then psi lambda 1 lambda 2 of x2. I don't know if there's a plus minus 1 here, but you can work this out. And now, and for the rest, let's say I1 to In, this is 0 identically. If these components are not identically all 1 or identically all 2. So this is saying that in a matrix, it's only like a diagonal matrix, and in higher tensors, it's only like the diagonal one. All right, and I guess the claim is, maybe I can just write it here, is if I call this theta of f lambda 1 lambda 2, if I define this to be this little theta, which again is this tensor, and I convolve this with f, that this does the job. So yeah. So this really constructs our capital theta that gives you this inverse divergence of a function f for any of these projections that you have. Okay, and I guess it's an exercise to actually work out that this does the job. So there are a couple of things. You need to check that this equation holds, that if I take divergence n times of this guy, I actually get back my original guy, and it still preserves the support. All right, okay. Yeah, this is the same capital theta. Yeah, yeah, sorry, maybe I should have put this up. All right, any questions on this? Okay, so I won't get a chance to talk in more detail about this, what we call synthetic Littlewood Paley decomposition. I'm not sure why we chose that name. Well, okay, fine. But anyway, so this will be applied to functions f, which will be these type of Mikado type objects. So there'll be objects of the form that we saw, W, tensor W, for instance, or the cubic one in the energy inequality. So things like this. And all of these have the property that if you subtract the mean, that their mean 0, and moreover, they're periodic to some period which is given by lambda r. And moreover, like the highest frequency contained in this is lambda. So when you do a decomposition like this for one of those guys, you'll put this lambda n bar essentially something larger, slightly larger than this lambda here, so that this identity minus this really just acts as a mollifier, and you get very good estimates because f really has no frequencies above lambda. So this guy is basically like acting on f, it basically acts as the zero operator. So you get very good estimates on this. And this guy here, you can do something similar. You choose lambda naught to essentially be something lower than the periodicity. So if I were to actually write the final term, which is just p lambda naught of f, then this guy would again act as the zero operator because it's lambda r periodic, and if lambda naught is chosen something slightly below, then this basically vanishes. So all you're left with is essentially terms like this, and for all of these terms, you can get the inverse divergence of that you want. All right, and maybe just the final part of the exercise is to show some estimates on this guy. So now we assume f is of this form. So no, actually, let's take a step back. Let's assume f is of the form that we had in yesterday's exercise, which was this intermittent Mikado that we constructed, right? So if you remember, so this was just something in one dimension. This was something in one dimension, and it had the property that it was, let's say R to R. It was L2 normalized to 1. Then it was periodic, lambda r periodic, and was supported in essentially minus lambda inverse to lambda inverse. Right? So this was from yesterday's exercise. And okay, well, here I just described what one needs to do in 2 dimensions, but it's very easy what one can do in 1 dimension. One does exactly the same thing, and one just has this. One doesn't have this additional term. So one can do exactly the same thing for 1 dimension, and you have an analogous guy here, which satisfies now that dx to the n of f is this f, right? And what I want is now an estimate on this. So I want to say that if I take the LP norm of this is given by, yeah. So firstly, what would you expect? You'd expect that because this you have taken divergence inverse a bunch of times, you would have gained, right? So this, you should think of essentially at frequencies between lambda 1 and lambda 2. So when you take inverse divergence, you'd hope to gain at least the lowest frequency. So you'd hope to gain at least lambda 1. So lambda 1 to the n. Right? And then it's like the LP norm of this projection. And now f had some intermittency. Remember that we had that f in LP, so this was part of the exercise. This is like r to the power, what was that? 1 p minus 1 over 2, right? Let me write this slightly in a different way as lambda over lambda r over 1 over 2 minus 1 over p. This is exactly the same. And now I'm saying that I have changed the highest frequency of this f here because I projected it to something which starts, its highest frequency of this guy is now lambda 2. So I would guess that the intermittency that I would get here would be something like lambda 2 over lambda r to the 1 over 2 minus 1 over p. And this is another exercise. So this is again slightly hard. We can discuss. What ideas you have. But yeah. So this should be a lambda 1. So yes, thank you. That's a good question. So this guy is the lowest possible frequency. So you have lambda r, kind of very low. Then you have lambda 1, and then you have lambda 2. And then you should think of this lambda being the largest guy. Yeah, thanks. Sorry? Yeah, f is infinitely differentiable. Yeah. So maybe it's good to write that. F is smooth and compactly supported. Yeah. It's only here where f is just smooth, it need not be compactly supported, and the reason for that is what we really want at the end of the day is functions on the torus on T3. And the way you can get functions on T3 is like you just extend to R3 and make it a periodic function of R3. So this f should really be thought of as a periodic function on R2. All right. Any questions on this? All right. So let me know how it goes with these exercises. Yeah. Cool. Okay, so now let's move on to the localized inverse divergence. Okay, so the setting is that you have some, let's say, vector field or tensor field. Let me just call it U on the torus. So, yeah, U. Right? And what you would like is to, in some sense, find a function, divergence inverse of U, under certain conditions. So this is some function or some other tensor, let's call it V, such that divergence of V will equal to U minus its mean. All right. Okay. And okay, there's a way to do this, and this is by Fourier multipliers. So this I think you'll see in the other lectures. But the issue with this is that this will not preserve spatial support. And what we had discussed last time is we really want an inverse divergence that does preserve spatial support. And in order to do that, we start with just an application of the product rule in calculus. So if I have a function and this vector u, or let's call it this vector v here, which is the divergence inverse, say we were able to find that, then this guy is simply fu plus grad f dot. So that's it. And so now one can guess that what we wanted was an inverse divergence. And so you can try to plug in the inverse divergence on both sides. So you have this guy. So this equation I'll put in inverted commas because I've not yet defined what the inverse divergence is. Fu. This I want it to be essentially like minus Fv plus, Fv minus divergence inverse. Right? And this is something you can make precise. So you can actually have this as a definition. So this is a definition, and so you have this. But here you don't know the inverse divergence, but here you can just use the usual, a usual inverse divergence operator that you already know, like the one coming from Fourier analysis. And then this would be an equality. And the advantage is up to leading, this is the leading order term here. And if I know already that V has a good support, so the support of V is the same as the support of U, and this is what we have been seeing in all of these exercises. We are constructing primitives of F so that if you take divergence a few times of that, you get F and you preserve the support. So think of U or V as something like that. Then you know that this V has the good support property. And so Fv has essentially the same support as Fu, right? So you have the support, but now you have this additional term, which again, you don't know how to control. But now you can apply this trick, and this trick appears a lot in, I guess, mathematics. It's just called, a parametrics expansion. You have something, you have defined something in terms of something good and in terms of it itself. And so now you can repeat this process by using the same ansatz for this guy. And so what you can now say is this is equal to Fv minus, now again, I apply the same formula for inverse divergence here. So here I'll have this, but now the divergence inverse only hits V. Okay, and now I'll have another term, which is divergence inverse. Now I'll have two derivatives on F, and then I'll have divergence inverse. Right? Again, this is something you can make sense of, but we'll see now that in order to get good estimates, it's worth propagating this quite a bit. So in the end, we'll get terms that look like essentially, let me write the leading order term, but then essentially it is some number of derivatives on F, and then some number of inverse divergences on V. And so n equals 1 to say some capital N, or maybe capital N minus 1. And in the end, you have a term. And for this final term, we'll just use the usual inverse divergence operator, which comes from Fourier analysis, which I'll call mathcal R. And this would be n plus 1, or capital N F, and then divergence to the minus n plus 1. Right. And this we now make as a definition. And you can check that if you actually apply divergence to this guy, that you get back that. So it is actually an inverse divergence operator. All right, and now what's the advantage of this guy? The advantage is all of these terms have the same support of Fu if you know that all the inverse divergences of V, so here we should again be thinking of F as being the slow variable and V as being the fast variable. So V is basically one of these guys or just the usual Mikado or something like that. And so this exercise tells you that you can indeed take these inverse divergences of this guy, which have the correct support property. And that tells you that this entire guy has the same support as this. Okay, but all of this would be completely useless if we didn't know how to control this. If we didn't know how to control this, and this again is using the old inverse divergence operator, this one will have no support. And so if we can't bound this well, it would be quite horrible. Okay, so let's try bounding this guy. So for this, we'll have some assumptions. So let's say, let me call this how to bound terms. Okay, so now we'll actually put some assumptions for this. So far, all of this was just algebra. There's nothing happening. Okay, so F will be a smooth function which satisfies the following estimates. That if I take, let's say, n derivatives of it, and let's measure it in L2. Let's measure it in LP. This is going to be bounded with some constant depending on P of lambda naught to the n, right? And this U will be something which is periodized with period larger than this lambda naught. So U is, let's call it lambda 1 periodic. I should put an inverse. Right? And also, let's say that U satisfies, it's basically just a function supported at that frequency. And this is something which you can assume. I mean, previously we were talking about all of these intermittent guys which had this whole frequency range. But once we really project to the individual frequencies, then with the choice of these lambda naught and lambda 1 being sufficiently close to each other, let's just assume that this U is essentially just concentrated at this frequency as well. So again, so we have this lambda 1 to the other. All right, and now maybe let's try to just bound the leading order term first. So leading order. So F V, this in LP. So firstly, by the decoupling lemma that Hyunju talked about, this guy is going to be bounded by the LP norm of F and the LP norm of V. Right? So yeah, good question. So P will be between 1 and infinity. I guess you can include infinity as well. So, no. Yeah. So we have this. And now you know that V is one inverse divergence of U here. And U was supposed to be one of these, came from one of these guys. And so when you take an inverse divergence, you'd gain the frequency, you'd gain the periodicity of this. So you'd gain 1 over lambda 1 of F LP, and then U. And so this is the gain you get by inverting the divergence. All right, and let's talk about the lowest, the remainder term. Okay, the remainder term, we have absolutely no control on its support. So it can really interact badly with all of the previously added perturbations and pipes, and it's all a complete mess. And so the way we deal with this is to make it as negligible as possible. So we'll actually just measure it in L infinity. So we'll measure this guy. L infinity. And okay, now this thing is something low frequency, which is supported, which is lambda naught, and this is high frequency, which is lambda 1. So this is basically high frequency at lambda 1. And so by, I can just do the most sloppy estimates. I can just remove this and just add a lambda 1, let's say, and then I need to estimate this. And since it's L infinity, I can just put L infinity on both of them. Right, this. And now, again, so this one cost n derivatives. So this is like lambda 1, and this was lambda naught to the n. This one now gained me n of these guys. So this one gained me lambda 1 to the n. So let me call it lambda naught over lambda 1 to the power n. And then I lose, say, one more here, but okay, fine. V has also gained, but no matter. Let's decide to lose it. It really doesn't matter. And now you have F in L infinity and V in L infinity. Okay. But we can't really use these estimates because these here are in LP. So we use Sobolev. And so we bound the L infinity norm of F and V with some fixed number of derivatives of norms of U and F. So this guy we can bound now by, say, lambda 1 here square, and lambda naught over lambda 1 for n. And now I can put actually LP norms. But the cost of putting LP norms here is I need to pay some derivatives of F and G coming from Sobolev. And okay, I've not really specified P, but I think the worst it can get in 3 dimensions is 3. It's some fixed number, so let me maybe call it a constant. Let me call it a constant here. And let me also absorb this into this constant. All right, so we have this. And the idea is this guy can be made super, super small. This guy can be made as small as I want. This guy can be, let's say, lambda 1 to the minus 100 if I want. And this is because we are going to use a super exponential scale of frequencies. So say I had just an exponential scale of frequencies, so where I called lambda q some fixed lambda, say lambda bar to the power q. Then this guy here would just be, this guy here would just be 1 over lambda bar, right? 1 over lambda bar to the power of n. Whereas this guy here would be some lambda q, right? And lambda q is lambda bar to the power q. And this q can be very large. And so if n is supposed to be fixed, and I want n to be fixed in my iteration, this is not going to be small. Like as q gets large, this will just completely eat up this. But it turns out that if you use now a super exponential answer, so instead of this, use lambda q is going to be your lambda bar to the power b to the q. Then actually you can close this. you can always close this, as long as like b is larger than 1. And you can find an n which is independent of q, which does this. And you can really make this as small as you like. And so it's a term which will not bother us at all. And so that's how we deal with the remainder terms. So what we have achieved is we have achieved an inverse divergence of this product of a high frequency term and a low frequency term in a way such that the leading order terms all preserve the correct support, and there's a remainder term which can be made as small as you like. Right. And yeah, any questions on this? So this is, sorry. Yeah, there's a lambda 1 here.
Why do you lose so much?
I mean, you don't lose this much. You can put an alpha. Like, it really doesn't matter. It's the sloppiest estimate. Yeah, but Ujjwal is right. I mean, to point this out, in some places you really need a sharp estimate on this. And this guy is essentially given as a kind of like a Fourier multiplier. So the problem is that in LP norms, it's fine. You can just estimate it. But if you're measuring in L infinity, then you'll incur a little loss coming from the fact that, yeah, these multiplier theorems like don't really work in L infinity. You'll see some loss. Okay, so that was this. Yeah. Sorry. This I have really sorry for the confusion. So we should think of applying this through the perturbation, right? So we should think of applying this to one of our error terms. So let's say the oscillation error or the transport error or something like that. In that case, this f will be something which is at the low frequency. So this was the A, and so this will be at lambda q frequency. And this guy will be the Mikado. So this is the high frequency, and so this will be at lambda q plus n bar or something. And so that's why actually like these like when you are applying this, these depend on q, and yeah, that's why. All right. For each iteration, it may vary. No. This doesn't. Yeah, okay, fine. The estimates depend on q, of course, but the constants in all of these inequalities and this n, all of these are independent of q, and that's quite important. Otherwise, you could run into a scheme where, okay, fine, every term you estimate is small, but the number of terms grows in q. So when you sum them up all together, then you'll actually might have something which is large. So that's the problem. So it's quite important. I mean, you can relax it somehow, but most convex integration schemes that I know really keep all of the number of terms and stuff happening in the iteration independent of q. Okay. Okay, so maybe one more thing you guys can do as an exercise is this guy here. I wrote it independent of the flow map phi. So in reality, you won't be taking the inverse divergence of f and u. You will in reality be taking inverse divergence of f, and then this high frequency function phi u you'll be composing with the flow map. So this is some diffeomorphism. And the exercise is to compute just do the algebraic manipulation for this when you actually have a flow map in place. So this is no estimates, this is just algebra, but it's just to get you, I guess, used to trying to do some Einstein summation and stuff like that. Okay. So now let's move on to dodging. Can I erase this? So let me recall from last time what we want to prove. We want to propagate the following inductive estimate. We want, if I take a ball of radius, so a ball around the support of one of my perturbations, W q prime, of radius lambda q prime plus n bar inverse. If I intersect it with a ball around the support of WQ double prime with radius Q double prime plus n bar inverse, this is empty if 0 is less than Q bar minus Q double bar less than equal to n bar. So this is what I wrote last time as effective dodging. And this is what we want to give some idea on how we can propagate this. All right. So what does this mean? So by propagating, we are now constructing something at WQ plus 1, and then we want to show this. So want to show basically this. Intersect the new one, which we are going to add. This is empty for Q prime between, I think it ranges from Q minus n bar to Q. Okay, so this is what we want to show. All right, and so if in our inductive scheme we have no idea what this is, so this is stuff that has been added previously in our iterative procedure. If we have no idea what this is, there's no way we are going to be able to prove such an estimate. So we need some inductive assumptions on what this guy is, and what we need to propagate. And so the assumption that we need is, maybe I can write it here. Actually, no, let me write it here.
The interaction between current generation and previous.
Yes, exactly. So maybe let me just draw a picture just to remind ourselves. So this was the frequencies, and this WQ plus 1 is something which is designed to correct these errors at lambda q. So you have here RQQ and this phi QQ living at this frequency. You want to correct it with some perturbation which has its highest frequency at lambda q plus n bar. And the periodicity of this is given by the geometric mean. So this will be, let me write it as lambda q plus n bar over 2, right, at this frequency. So this is going to be the highest frequency of my WQ plus 1, and this is going to be the periodicity over here. Okay, and the things I want to avoid are all previously added perturbations. So there was one that happened at the Q minus 1 step, which was here. There was one that happened previously, which was here. And there are also like the really old ones, the ones which caused the obstruction to us, the ones which had their highest frequency between lambda q and lambda q plus n bar, like so. And the things that are okay, so the things that we are allowed to have intersection of the support or interactions with are all the velocity fields whose highest derivative is less than lambda q. And this we called uq hat. Right, so these were the velocity fields that if we had interactions with WQ plus 1 here, and if we flowed by this velocity field, we got the correct estimates for the transport and Nash errors. But we don't want any interactions between these guys and this perturbation we're going to add. Because if we had so, then our error estimates would just break down. So that's what we want to show. So these orange guys indicate these velocity fields, and this white guy indicates this one, which we want to construct. All right. Can I erase this? So I don't see the time. That clock is not working. Okay, I don't. Does that mean I have half an hour? Okay. Okay, this is going to be okay. Okay. So the assumption we want to propagate on these old guys is the following. Okay. So all of these guys, you know, or at least this is the heuristic, is that if I take lambda q bar, it's going to have highest frequency at lambda q plus n bar. So if q bar is something here, then it's going to have that highest frequency. And it's going to be periodic with respect to the slower one. So that means if I consider omega in my torus T3 to be a convex set, whose diameter, the diameter of omega is less than or equal to lambda q bar q prime plus n bar over 2 inverse. So if it's smaller than the periodicity you expect, then the intersection between the support of wq prime and omega, this has a very precise structure. It's going to be a finite union where this finite number is just something which is constant throughout the iteration. And I'll comment about it in a bit. And it's going to be a ball of radius radius given by the highest derivative cost. I mean the high frequency. So lambda q prime plus n bar inverse. And it's essentially like these Mikado pipes. So these you should think of as straight lines. So let me just write L here for a collection of lines. And this I goes from, say, some fixed number 1 to some fixed number m. Okay, this is a slight lie because in reality, we'll have the flow maps moving stuff around. But as long as we are in like a ball which has a set which has diameter less than its length scale is much smaller than the length scale associated to the flow of this velocity field, you can really kind of imagine that this is basically a line. I mean, in reality, it'll be slightly curved with some exact Lipschitz constants, but this for simplicity, you can imagine it's just this. So this guy, so let me just draw a picture. So here's your, let's say, convex set. Okay, that's maybe not quite convex. Omega. And so there's a finite collection of disjoint lines. Okay, the LIs are disjoint. Li pairwise disjoint, though it doesn't matter. Actually, it doesn't matter. So there are these lines Li. And so these correspond to adding these Mikados in the different directions. And for a fixed kind of direction, you'll have only one, because you know that its periodicity is basically larger than this guy. So the next one, wherever it appears, is going to be outside this set. And so the only others that can appear are things which appear from things coming in other directions. So you remember we had like a set of directions psi. And from other technicalities in the scheme involving cutoffs and things like that. But in reality, we can propagate, or we can assume that there's going to be a fixed number m, which is independent of everything else in the scheme. Which is independent of q. That's the important part, for which this is true. So this is, and okay, fine. These have some thickness, and so that's the thickness of this guy. So this is going to be the structure of our WQ prime. And this will be an inductive assumption that we need to propagate. All right. Okay. So maybe let's try to use this assumption to show how we can get this dodging and how we can overcome this obstacle. So the main thing I want to convey is we had this obstacle where you had these very old pipes whose highest frequency was smaller than the periodicity of this guy. And so a priori, you will have interactions between them. Their supports cannot be made disjoint. But there's a way of modifying our ansatz for our perturbation in order to overcome this. So that's what we'll talk about now. So any questions about the setup of what we need to prove, and yeah, what we need to assume? All right. Okay, so we'll split this dodging into two steps. So one is we'll stay disjoint from these perturbations here, which I call the old ones, the ones which have their highest frequency smaller than the periodicity, and then we'll do an additional step to talk about these guys here. All right. So dodging old pipes. Okay. And yeah, okay. Yeah, so let's get started. So, okay, so we first modify our ansatz somewhat. So, yeah. So let's consider a cube of dimensions, let's say lambda q inverse. I'm calling this lambda q. I mean, we'll change this in a second. But the idea is we are going to now split up our torus into cubes like this. And the reason we are allowed to do so is we are going to have a partition of unity on each of these cubes and then going to glue them up all together. And the reason this doesn't hurt us is that if the length scale of this cube is basically of the frequency of the low frequency term, so we are going to introduce some cutoff, cutoff chi, which is indexed by, let's say, which cube you're at. So maybe let me call that L. And we are going to add this to the ansatz. So now W is WQ plus 1 is going to equal, so we already had this AXI, RQ and phi Q. And we had this, the Mikado, which we had, and this was composed by the flow map. But now we also have this, this cutoff function, which I call IL. And the reason this doesn't, sorry? No, this is a space cutoff. This is a cutoff which is basically divides up the torus into these bunch of these cubes. So this is a partition of unity. It's kind of non-trivial. I mean, like, what partition of unity? Do you want it normalized in L2 or L3? But these are things that we can talk about later. It's how we get the cancellation for each of the terms. Okay, and the reason this doesn't hurt us is this still has derivative cost, which is coming from lambda q. So if you have derivatives hitting this or this, they're costing only lambda q inverse. So this is okay. All right, and now the way we saw is that, okay, fine. In this cube now we have all of these old pipes. You have all of these guys floating around, and whatever. It's just a mess, and so on. You have all of these guys floating around inside. And what we saw from this obstruction is that you cannot place a periodic set of of pipes whose highest frequency, or of lines whose periodicity is given by this lambda q plus n bar over 2, because it is just larger than the thickness of this. So if you were to try to place, say, some lines here of some periodicity which is much smaller than the thickness of these guys, they are going to intersect, and this is going to be the problem. Okay. So the first step is to now identify a subregion of this region where there are no such pipes. So we want to identify a subcube, or subregion of this, for which none of these supports of these perturbations actually intersected. All right. And so the way we are going to do this is, okay, so now let me cheat a bit and just change this to lambda q plus 1. And okay, I'm going to do a bunch of things, and they are in some sense unmotivated because there's a lot of flexibility in doing this. But what I'm going to do now is I'm going to cut this up into some cubes. And maybe I'll have one more set of cubes. All right. Okay, such that the length of this guy will be lambda q plus 1, and then gamma q inverse. I have not told you what gamma q is, but I'll do so in a sec. And this guy here is going to be, say, lambda q plus 1 gamma q to the 4. I think this works. Okay. So gamma q is just going to be something, a very small power of the ratio of lambda. So let me write this here. So gamma q, you should think of it maybe as lambda q plus 1 over lambda q, or lambda q plus n bar over lambda q to the epsilon, where epsilon is something so small. Okay, let's just do an ansatz. So if epsilon was something like 1 over n bar, right? Epsilon is like 1 over n bar. Then this means this is kind of like lambda q plus 1 over lambda q. Right? I mean, this is true if you're using the exponential ansatz. It's not quite true when you're using the super exponential ansatz, but you can still say that these are approximately the same. But this is already too large for us. So we really want to make this small. So maybe an appropriate choice to think about for epsilon is like 1 over n bar square. So something, in some sense, a very small ratio of these guys. Okay. And let's concentrate on one of these green cubes for a second. All right. Okay, so on a green cube, so I'm having this grid just in this plane, but what I'm doing is I'm just extending it to a cube in this direction. But in this direction, the length is always going to be lambda q inverse. Right? It's only in these two directions where I have this fine subdivision. In this direction, I'm just going to have the largest length. So these are like very anisotropic cuboids. So on a green cube, we first now count how many of these pipes, for instance, how many of these velocity perturbations, their support intersects this cuboid. Okay. And now, by assumption, this cuboid is indeed a convex set whose diameter is less than the periodicity of these guys. Because remember, the velocity fields we want to avoid are the ones which have their highest frequency, which is smaller than the periodicity. But that means that their periodicity, their own periodicity, is going to be less than lambda q. So their own periodicity is going to be less than lambda cube. And so that means that this guy here is going to be less than lambda cube. And so that means that at most like a finite number of these can intersect this guy. Okay, so only a finite number intersect. It's called bounded. Number of pipes intersect. Okay. And now what we want to do is take any of these pipes that intersect this and just project it onto this green square over here. So I just want to project it onto this green square, and I want to count how many of these smaller squares are intersect this projection. So let me, maybe this, okay, this is quite a bad drawing. I mean, this will be much, much smaller than this, but I mean, you should really think of this green square as something here, and this has been subdivided into something quite small. And it's like you're looking from this direction into all this mess. But you know that there's only a bounded number of pipes in this mess. And what you do when you see is you see things like this. And what I want to do is I just want to count the number of these squares that intersect. That intersect this projection. Okay, so the number of such squares can be given by, now we use the second property of this assumption that these guys are basically lines, right? And these lines have been thickened to their to some thickness, but this thickness corresponds to the highest frequency of this guy. But this is always going to be much, much larger, or larger than lambda q plus 1 times this gamma, or whatever that thickness was. So actually, the way I drew it was quite wrong. Maybe I'll redraw it. So you have this green cube. You have subdivided this into these smaller ones. But now the thickness of each of these guys is actually much smaller than this length scale. So in reality, it just looks like a bunch of lines like this. Like that. And so you can now see that the number of such squares is really given by the length. The order of magnitude is given by the length of this guy. So it's basically the number of squares in like a line. So that's going to be this one here, lambda q plus 1, gamma q to the 4, over this length scale here, right, which is lambda q plus 1, gamma q, and this is basically lambda q cube, right, a gamma q cube. Okay, all right, and okay, so now I'm going to, so what I want to find now is I want to find, so now, okay, fine, it's quite clear that there are positions I can place my pipes in, right, because they're gamma q cubed, but the total number of cubes in this is gamma q cubed squared, right, because they're gamma q cubed here and gamma q cubed here. And so it's quite clear that you can find some place here where you can place all your pipes. Okay. But that's not what I want to do. The reason I divided up into these green cubes is I want to have something which is periodic. So what I'm going to do now is I take all of these green guys on which you have these projections and just imagine them as just being on one guy. So just shift them onto one. Okay? And so then the number of squares that are occupied, if you superimpose all of these guys onto one, is just this number. It's just this. So upon superposition, you have this number, which was gamma q cubed. But that was for each of these green squares. And the number of green squares is again given by this over this, or sorry, this length scale over this length scale. So that's how many of these green squares there are. So that's lambda q plus 1 over lambda q plus 1 gamma q inverse. And so that just gives me another gamma. So gamma q to the 4. So that means I can superimpose each of these guys and still find plenty of room because they're gamma q to the 6 of them. So I can find some place here where in that cuboid there is no intersection with any of these guys. All right. Okay, so what that means when I translate it here, when I unsuperimpose it, is that there is a periodic bit. So this guy, maybe it's this guy, this guy, this guy. Yeah, so just it's periodized because it's all in the same position. Upon superimposition, when I did the superposition, I found a place. So when I put it back, it's all periodic. So here, here. All right. So now I'm going to modify my ansatz somewhat. I'm going to, so I had this chi L, which was a cutoff suited to this box. But now I'm going to, sorry? Now I'm going to have an additional guy, which is essentially, you should think of this as a very thick Mikado, which is basically concentrated here. So let me call this this guy rho, and now I will have the W. Okay, and then this all of these will be composed with phi. So now I have achieved what I wanted to achieve, in the sense that the support of this guy is contained in the support of this row, right? And the support of this row is these blue squares here, and these blue, okay, not squares, these blue cuboids, and these blue cuboids have this property that they are disjoint from any of these bad old pipes that we wanted. Okay. But it does turn out now that W is not actually lambda q plus 1, so lambda q plus n bar over 2 periodic, right? Because there's the row which cuts it off. And it cuts it off at some other scale here. And these blue guys don't form a partition of unity. So, I mean, you're kind of changed the way you're doing your cancellation. So the way you now do the cancellation is as follows. So now we want to again say WQ plus 1, then say WQ plus 1. Okay. And the way we expand this is, okay, we have the term that we want to do the cancellation, which is this a square psi RQ psi tensor psi, essentially. I mean, there are all the flow maps and stuff, but let's ignore that. So there's this low frequency term for which we want, this is basically RQ, and this performs the cancellation. And now you have the term, which is a square psi. I'll stop writing this here. Psi tensor psi. And now you have this. Okay, so this chi L here, I'm going to take it as a partition of unity, which is square summable to 1. So that's why I did not see it in the first term, but I will see it here. Chi L square, and then this rho square minus 1. So the 1 will now then remove this, and then there'll just be a chi square L, and this is a partition of unity, so this gets cancelled, and so you just remain this. So this cancels with this minus 1. So you have that. Now you have square psi tensor psi, and now you have your Mikado, and which is W square W tensor W W square -1. And so this is what we had previously without all of this. But now we have included this, and that gives rise to another term. And this term, you can see, lives at frequency lambda q plus 1, because that's the frequency of this. So in reality, what's now happening n bar is, okay, we have added some perturbation here, which has highest frequency here and periodicity here. So when we take some nonlinear combination of it, such that squaring or cubing, then we have errors which occupy all of this region. But now we have one more error here, which is new, which occupies this region at lambda q plus 1. And so we'll need to do an error estimate on this guy. Okay, so maybe, what's the time? Let's do that briefly. So we want to do the error estimate on this. So essentially the same game. This is like an oscillation type error. So we have the error it generates, oscillation error. Is going to be divergence inverse of, so when I have this gradient that hits all of this guy. So I have gradient of a square, psi square, and this chi L square dot psi tensor psi. And now I have, this rho square minus 1. Okay, and I want to estimate this, say, in L3/2. Okay, now again, from our localized inverse divergence, we can put the divergence inverse just on this. That would be the leading order term. But now you kind of notice a problem. So this is just at frequency lambda q plus 1, modulo some of these gammas, but let me ignore these gammas. So these guys are basically at frequency lambda q plus 1. The size of this is delta q plus 1. Okay, there's a factor of intermittency coming from the fact that this is intermittent. And you're measuring it in L3/2. Okay, but now this looks very scary. You have this gradient which is hitting this chi L. And the chi L, remember, was this partition of unity. Sorry, this partition of unity, and I chose this length to be lambda q plus 1 inverse. Right. So a priori, you'd only get lambda q plus 1, and this gives no gain. So these completely cancel, and this is the same as the size of RQ, but this now has to live at the frequency lambda q plus 1. So this has not gained anything, and this seems problematic. But the thing here to notice, and this was first noticed, I think, okay, maybe, I don't know. The first place I know where this was noticed was in the work of Matt Novak and Vlad Vikram, where they showed H1 half intersect L infinity solutions to Euler, is they use this idea. And the idea is basically, okay, you have this gradient, but it's dotted with psi tensor psi. And psi here in this picture is this long direction. So that's the direction where you're adding the pipe. It goes, the cuboid is the pipe. And so actually this gradient is not seeing the full gradient, but just the gradient in the long direction. So it's just the cost of this cutoff, the derivative cost of this cutoff in this long direction, and that is lambda q. That is still lambda q. And so you see here from noticing that because you're dotted with chi tensor chi, because you're dotted with chi here, that you're only seeing this and not the perpendicular directions. And that's the gain that you need in order to make this close. Yeah, that's the reason we use okay, that's the reason why the anisotropic guys work. The reason we need them is because we have this kind of like half amount of intermittency. So there was this previous work of Tristan, Nader, okay, Buckmaster, Masmoudi, Vikol, and Matt Novak. And there they were able to construct H1 half solutions of Euler. So maybe I should write this. Master, Masmoudi, Novak, Vikol, H1 half minus solutions of incompressible Euler. So this is without the local energy inequality. So there's no third equation, there are no current errors. All they want is just a non-unique solution of this guy. And there, they did not have anisotropic cutoffs, but that means they had to use quite a lot of intermittency here in order to make, like all of this, like kind of counting argument, counting the number of squares and then seeing if there's room available. That really works if you have lots of intermittency. If you have too little intermittency, then it doesn't work. So they had this. But then Novak and Vikol extended this to H1 half minus intersect L infinity minus solutions. And here, if you want to get the L infinity, if you want to get the solution to be almost bounded, then it is crucial that your intermittency is not larger than this ratio of lambdas to the 1/2. If it were larger, then from the heuristics Hyunju showed you, you'd see that, yeah, you can't bound the L infinity norm. And if it's too small, then you really don't have enough room to play this sort of game. So it really seems that this, at least for the way we are approaching this problem, this seems to be the only value of intermittency that works. But then we are forced to use these anisotropic cutoffs, this idea from their paper. And the idea works simply because, yeah, in the oscillation error, you're seeing this long direction, not the short one. All right, so that's kind of how you do that. I think I'm out of time, basically. So maybe I'll stop here.
There are two really different types of oscillation error. In comparison to the classical scheme, you have this extra different types of oscillation.
Yeah. So you have these guys which are quite intermittent. So the one at this shell is like fully intermittent. Then the exercise that I showed in the beginning shows that like as you go down in shells, the intermittency gets smaller and smaller. And the thing here has almost no intermittency. But now you have this new error here, which is again has almost no intermittency. It has some intermittency coming from these gammas, but it's actually quite small, which lives over here. But it's still just an oscillation error, and you handle it in the same way. So it's nothing. Yeah.
Other questions or comments?
Okay, maybe I have a few questions. So this is part one of the dodging, in the sense that I kind of sketched how you can avoid these very old pipes. But now you get to pipes whose periodicity is larger than lambda cube. And then in this cube, you can have many of them intersecting, because the periodicity is much smaller than your convex set, and so there can be many. And so you have a different argument to deal with these guys. So these now will be like how we are going to place this. So this part of the argument is like deciding the placement of rho in order to avoid these old guys. But now you want to do the placement of W. The argument for this is somewhat similar to this. It's going to be some counting of cubes, but the cubes will be of different sizes and different parameters. And I don't know if you guys want to see this. So I can do that, or I can talk about the pressure increment, which is this new thing, which is, I think, I don't know, it's this technical difficulty which exists only in our scheme. So I don't know if you want to see that either. But let me know, like, what would you guys prefer to see? The pressure, or sorry. Okay, the pressure. Okay, so we'll talk about that. So maybe we can discuss this like outside if someone's interested on how to do something like this to avoid these guys as well. Okay, there's also the additional thing to check that once we have constructed the placement for all of these objects, that this assumption is still satisfied. That's another small argument.
Okay, thank you.